Good morning, everyone. How are y'all doing? I am tired. I don't know what it is, but I am very tired. No. Okay. Okay. Alrighty. Also, so I graded the quizzes. Gonna grade the homeworks today. In the future, I'm gonna grade those over the weekend. It was a ridiculous week last week, but this week I will grade the homework and quizzes over the weekend. So I haven't made the comments visible yet because I was waiting for a couple people to submit. They were either missing pages or didn't have a file. So I was just waiting for those to get submitted to release the comments for the quiz, but those will be done soon. Yeah. Okay. Alrighty. So before we start talking about Green's theorem, I'm going to do one more example for a surface integral of a vector field, and then I'll do sort of a really quick recap with the stuff you should have memorized essentially for surface integrals. Okay, so we'll do one more example. All right, so let's calculate the flux of x squared times j is our vector field. Over the surface y equals 1 plus x squared plus z squared with y between 1 and 5. And the orientation is going to have normals pointing in the negative y direction. So not directly in the negative y direction, but it's just like saying an upward pointing normal. Except now we're saying instead of upward, meaning the z component is positive, negative y pointing normals means the y component is going to be negative. Okay. So don't really need to sketch here, but it's going to look something like this. So here's y equals 1, here's y equals 5. And, well, we'll look at this in a sec. Actually, sketches is nice to have. Okay. So this is our surface S already. Okay, so we need to parameterize our surface. And there are different ways to do this. The easiest one is to do it as the graph of a function, except it's not z is equal to a function of x and y. Now we have y by itself, and we're writing y as a function of x and z. But we use exactly the same idea to parameterize it. So we do the same thing. So we say y is equal to a function of x and z. And so we let x be x, z be z, and then y is that function of x and z. So x is x, y is the function of x and z. So 1 plus x squared plus z squared. And z is z. And then we have to specify where the parameters x and z live. So we're going to do the same thing we do for a graph of a function. We're going to project to the xz plane and look at the shadow of this guy on the xz plane. And that's going to be where x and z live. That's going to be the region D. Okay. Okay. So the book does this a little differently. It jumps immediately into polar. We're going to do that after we write the integral down. I find that's a little easier, but that's fine. Okay. All right. So we've parameterized it. We'll figure out the bounds once we switch to polar. But any questions about how this parameterization works? Does everyone see where this comes from? Right, we got one of the variables by itself. It was not z, it was y this time. And we wrote it in terms of x and z. And so we let x be x, z be z, and then y was that function. So that's how we parameterize this guy. Okay, so the next thing we need to do is we need d vector s. Okay, so I'll give you a shortcut. I'll summarize this later. Usually we're just going to have z is equal to a function of x and y for graph of a function, but this is going to work exactly the same way. Let me in fact tell you how that works for there, and then I'll show you how this is pretty much the same thing. So for z is equal to a function of x and y, the way we parameterize is x is x, y is y, z is that function. And x and y lie in the same region D where they lied in, because x and y are the same, x and y. Okay. Okay. So in that case, if we want the upward pointing normal, then d vector s, so the n of xy, the normal, is going to be negative g sub x, negative g sub y, 1. So that's our upward pointing normal. So g, lowercase g is going to be the function that we're the graph of. And the first component is going to be negative the derivative with respect to x of that function. Second is negative the derivative with respect to y. And the third is going to be 1. A z component is 1. And that's upward pointing because the z component is positive in that case. In this case, we don't have z is equal to a function of x and y. We have y is equal to a function of x and z. So in this case, we let x be x, y is the function of x and z, and z is z. X, z lives in the region D. And then if we want positive y pointing normal, in this case we want negative, so we'll flip it. But if we want the positive y normal, so the variable you have by itself, right? And the first one, it's z equals something. If we want the positive z pointing normal, this is what we get. Here we have y equals a function of x and z. If we want the positive y normal, we do the same thing, except the first component is negative the derivative with respect to x. Second is 1, because y is the variable by itself. And the third is negative the derivative with respect to z. And then you can guess what we do for x. It's exactly the same thing, except for the normal, the x component's 1, the y component's negative g sub y, and the z component's negative g sub z. Okay, so in this case, we want negative y normals, and we already parameterized our guy here. So d vector s is going to be, so the thing right above, the negative g sub x, 1, negative g sub z, that's a positive y pointing normal. We want a negative y pointing normal, so we need to flip it, flip the sign. So it should be g sub x, 1, sorry, negative 1, g sub z. And in our case, our g is 1 plus x squared plus z squared. So we get 2x, negative 1, 2z. Whoops, sorry. And then times dA. Because we want a negative y pointing normal. You can calculate this pretty easily, but it's nice to have memorized if you understand where it comes from. Okay. So we have our d vector s. Let's put everything together. So we wanted to integrate, our vector field was 0, x squared, 0. And so we're now going to integrate over the region D where x and z live. And our vector field 0, x squared, 0, when we replace x, y, and z with the parameterizations, remains 0, x squared, 0, because x is equal to x in our parameterization. So it's our vector field f when we place x, y, and z with the parameterizations. And then our d vector s, we said, becomes 2x, negative 1, 2z, dA. And so when we take the dot product, we get 0 minus x squared plus 0. So we're just integrating negative x squared over the region D where x and z live. So now we need to figure that out. Okay, so let me redraw our picture here. Okay, so we need to look at the shadow of this on the xz plane. So the widest part of the shadow is clearly going to happen here at y equals 5. So y equals 5, we have 5 is equal to, that's y, 1 plus x squared plus z squared. Or in other words, x squared plus z squared equals 4. That's the shadow on the xz plane. That's the outer bit. So in the xz plane, we look at everything inside the circle. X squared plus z squared equals 4. Okay. So now we want to switch to polar here. So forget about everything that came before. We're just interested in this double integral here. So this double integral, the region of integration, D, is best described using polar. So we're now going to switch that double integral to polar. So in polar, R goes from what to what? Zero to 2, exactly. And theta, of course, goes from 0 to 2 pi because we're going all the way around. And so now it's x and z. X is the horizontal guy. The horizontal guy is going to be r cos theta. The vertical guy is going to be r sine theta. So negative x squared becomes negative r squared cos squared theta. And then dA becomes rd rd theta. Okay, so I don't want there to be any confusion here. So the way the book does it is a little different. They do cylindrical from the get-go. And then the the sort of RD theta is kind of built into that, but I like to just use a graph of a function and then go to the integral over the region D, dA. And then now we just have a double integral. And then the region D is best described using polar coordinates there. And then we switch to polar. And when we do that, dA becomes RD theta. OK, so that's just negative r cubed cos squared theta, RD theta. And that is not a difficult integral to do. And we just get negative 4 pi. OK. Any questions about this example or in general? And I'll give you a couple things to have memorized that will make your life make things a lot quicker for calculating these surface integrals. Okay. So here are a couple things that pop up a lot, and you'll save a fair amount of time if you have these memorized. So if you need to parameterize sphere of radius r centered at the origin, just remember, use spherical coordinates, but let rho be r. So x is going to be capital R, sine phi cos theta. Y is going to be capital R sine phi sine theta. And z is capital R cos phi. And the bounds for phi and theta depend on whether you're getting the entire sphere or just a hemisphere or etc. Some other piece of the sphere. But you can figure out the bounds for phi and theta. But yeah, use spherical coordinates, but set rho equal to r. And in that case, so if you're integrating a scalar function, d capital S is going to be the r squared sine phi dA, d phi d theta. Let me just write it like that, actually. So remember, R is going to be given to you in the problem. So you should not see a capital R in there. But think rho squared sine phi when we switch to spherical. You're going to get the radius squared sine phi dA, which is d phi d theta. And the d vector S is going to be the same thing, except it's a vector now. And so you're going to be multiplying that r squared sine phi times the radial unit vector. And so it's going to be exactly your parameterization divided by r. And so it's just going to be, you get rid of the R in your parameterization. So sine phi cos theta, sine phi sine theta, cos phi. That's a radial unit vector, and then you're multiplying that by the R squared sine phi. Absolutely, absolutely have that memorized. That's going to save you a significant amount of time, and spheres pop up all the time. Way easier than calculating the g phi cross g theta and then simplifying. Okay, so that's a sphere. For sure want to have that memorized. The next one is the graph of a function, which is good to have memorized, but it's doable if you don't. So the graph of little g of xy. Oops. And let me specify, we're told x and y live in D. So the way we parameterize that, as we saw, is we let x be x, y be y, and then z is that function of x and y. And then x and y lie in the same region, D, as we were told before, because x and y are the same. X is x and y is y. So for scalar functions, ds is going to be the square root 1 plus the partial g with respect to x squared plus the partial g with respect to y squared dA. Good to have memorized, but you won't lose too much time calculating. And d vector s is, so, sorry, I forgot to mention, hang on, this is outward. If you want the outward pointing normal, for the sphere, this gives you the outward pointing normal. If you want the inward pointing normal, you need negative of this. Sorry, forgot to mention that. For the graph of a function, if you want the upward pointing normal, in other words, if you want the z component to be positive, you get negative g sub x, so little g is the function that we're the graph of, negative g sub y, 1. Obviously, if you want the downward pointing normal, you would negate that whole thing. Okay. So those two, good to have memorized. But any questions? All righty. So let's look at Green's theorem now. So moving on to the big integration theorems. Okay. So, okay, all of these integration theorems, Green's theorem, Stokes' theorem, divergence theorem, are going to relate the integration over some region to an integral over the boundary of that region. And we'll talk more about that when we get to the Stokes and divergence theorem. But Green's theorem is going to be the simplest one. So the setting for Green's theorem is we're in R2. Green's theorem has to be in the plane. Stokes' theorem is basically the three-dimensional version of Green's theorem, but for Green's theorem, we're in the plane. And C is going to be some closed curve. And we're going to give it the counterclockwise orientation. So there's C. We're going around it counterclockwise. Okay, so C has to be a closed curve. It needs to enclose a two-dimensional region. So D is the enclosed region. And this is our setting here. Okay, so what we're going to do is Green's theorem basically tells us how to take a line integral around a closed curve in R2 and turn that into a double integral over the enclosed region. So we know what happens if we integrate a conservative vector field around the closed curve C? What do we get? Right, if you integrate a conservative vector field around a closed curve, you always get 0. Remember, because we have the fundamental theorem of line integrals, basically, the closed curve starts and ends at the same point. So if you're a conservative vector field, you're evaluating the antiderivative at the start point minus, or the end point minus the start point. But they're the same point, so you should get 0. So Green's theorem tells us basically what happens if the vector field's not conservative. What do we get? So Green's theorem says all of this stuff. If C is a closed counterclockwise oriented, it needs to be counterclockwise oriented, closed curve, enclosing a region D, then we have the integral. Since it's a closed curve, we like to do the little circle there sometimes. So the integral on the closed curve C of the vector field F1, F2. And often, especially in this context, we'll see that written as the integral of F1 dx plus F2 dy. Those mean the same thing. That just means the integral of the vector field F1, F2. So that's going to be the double integral over the enclosed region D. It's a double integral because it's a two-dimensional region. And this should look familiar. The partial of F2 with respect to x minus the partial of f1 with respect to y. We integrate that over the enclosed region D. Okay, so this partial of f2 with respect to x minus this partial of f1 with respect to y, that you should remember from the cross partials condition for checking that a vector field is conservative on R2. So remember, if your vector field is conservative on R2, the way we can check that is we check that those two partials are equal. So the partial of f2 with respect to x minus the partial of f1 with respect to y will be equal to 0 because the two are equal. And that's a good way to remember the thing that you're integrating. Remember that cross partials thing. And then just remember the one involving the partial with respect to x is coming first, because that sign does matter. Okay, so that's Green's theorem. You have a closed curve, needs to be counterclockwise oriented. And if you're integrating a vector field over that, then you can use Green's theorem to turn that line integral around a closed curve into usually a simpler double integral over the enclosed region. I'll do this on the next page. Okay, so Green's theorem almost always so my goodness, we almost always use Green's theorem to change a line integral around a closed curve into a double integral. That's pretty much 100% of the time on an exam. If we expect you to use Green's theorem, you're going to start off with a line integral over a closed curve. Let me say in R2. So line integral around a closed curve in R2, you're going to use Green's theorem to turn that into a double integral over the enclosed region. We can go backwards, as we'll see tomorrow, but you kind of have to be clever in doing that. And the reason is that, so if you start with the line integral, you have your vector field. And then if you go to the double integral, we turn that vector field into this guy here, which is just some function of x and y. The thing is, if you go the other direction, if you start off with a function and you turn that into a line integral of a vector field, that function, there are infinitely many vector fields which f1, f2, where you can turn them into that function, the partial of f2 with respect to x minus the partial of f1 with respect to y. So you have infinitely many vector fields you can use. We'll see when we do area later. But it's much less common to go backwards from the double integral to the line integral. because it's more difficult to do that way. But it'll make more sense when we get to the area thing. But let's do an example of this. So let's do an example where we do both of them and we show that we get the same answer. So let's verify Green's theorem for the integral over the curve C of the vector field f, where f is going to be xy squared x is going to be the counterclockwise oriented unit circle centered at the origin. Okay, so really quickly, we're gonna do the line integral, and we're gonna do the double integral over the enclosed region, and we're gonna show that we get the same thing. Normally, we would just do the double integral because it would be easier, but we're just showing we get exactly the same thing when we do both here. Okay, so let's do the line integral. So we have the counterclockwise oriented unit circle. Let's parameterize it. Okay, so unit circle going counterclockwise, how do I want to parameterize this? So I let x be what? So I'll let x be cos t, and I'll let y be sine t. X cos t, y sine t goes around counterclockwise. And since we get the entire circle, I'll let t go from 0 to 2 pi. Okay, so we're going to need r prime of t for this. And so that's going to be negative sine t cos t. Alrighty. And so we get the integral from 0 to 2 pi. Our vector field f, we replace x and y with the parameterizations. So xy squared, sorry, becomes x becomes cos t. Y becomes sine t, so cos t sine squared t. And then x becomes cos t. So that's our vector field f now. And then we dot that with r prime t. So that's negative sine t cos t dt. And we get the integral from 0 to 2 pi, taking the dot product. So we get negative cos t sine cube t plus cos squared t and so for the first term we can use sub, let u be sine t, du is cos t dt, and so we get negative u cubed, which is negative 1/4 u to the 4, which is so negative 1/4 sine to the 4t when we integrate that guy. And the cos squared t, we can use a half angle formula to get 1/2 1 plus cos 2t. When we integrate that, we get 1/2 t plus 1/4 sine of 2t. Going from 0 to 2 pi. And plugging in 2 pi and pi into everything involving sine here, we get 0. And then the 1/2 t becomes just pi. So when we integrate this line, when we do this line integral directly, we get pi. This example wasn't too bad, but we'll see some examples which are either impossible or just extremely disgusting evaluating directly. And in that case, using the double integral is going to be a lifesaver. But let's do the double integral. Okay. So if you need me to go back, I'll do that after I do this. But let me do the double integral really quickly. So that was our curve C. Let's look at the enclosed region D. That was our integral. Let's use Green's theorem. Green's theorem says that is equal to the integral over the enclosed region of the partial of f2 with respect to x. What's the partial of f2 with respect to x in this case? It's just 1. Minus the partial of f1 with respect to y. So the partial of f1 with respect to y, x squared y, differentiate with respect to y, we just get 2xy. And we integrate that over the enclosed region D. Okay, so obviously we're going to want to switch to polar, but before we do that, let's recall back to using symmetry to simplify our integrals. So we're integrating over the enclosed region D. Does it have any symmetries here? Is there symmetry about x equals 0, symmetry about y equals 0? Does it have either? No, this is the same thing. I've just wrote it a different way. That's our vector field, x, y squared, x. So first we integrated directly around the circle. Now we're integrating around the enclosed curve. And we're showing we get the same thing for both. In practice, you're only going to do the double integral in Green's theorem, but yeah. So do we have symmetry about x equals 0? Right, our enclosed region, yes, we do. Symmetry in the x direction about x equals 0, the y-axis, yes, we're mirror image left and the right. And then same thing, symmetry about y equals 0. So any x or y odd terms are going to integrate to 0 in our integrand. So we're integrating 1 minus 2xy. Do we have any x odd or y odd terms? We do. The 2xy is x odd and y odd, so that is going to 0. by symmetry. So really, we just have the integral over the region D of 1 dA. And what is that? Well, the integral of 1 over the region D with respect to area is, of course, just the area of D. And what's the area of D? The disk of radius 1. Just pi r squared, and the radius is 1. And so we are verified. We see when we did the double integral, we got pi. And when we did the direct line integral, we also got pi. Notice doing the line integral was more work in this case, and that's almost always going to be true. Doing a line integral is almost always going to be more work than doing a double integral over the enclosed region.
So what's the domains for the double integral real quick? Because it's dA. Would that be like, would that be like from 0 to 1, then 0 to 2 pi?
Yeah, so we would switch to polar if you wanted, if you forgot about the simplification thing and we had to evaluate this and we evaluated directly, then we would just switch to polar and we would let r go from 0 to 1, theta go from 0 to 2 pi. Whoops. And then we would, so 1 minus 2xy would become 1 minus 2 r squared cos theta sine theta. And then dA would become r d theta because we're switching to polar. And then when you do all that, you get the same thing. Yeah. But luckily, we don't have to because we could use the symmetry trick and then we just see we're just getting the area of the region, which we know is pi r squared. Okay. Any other questions? All righty, we'll do some more examples of this tomorrow. And I will see y'all later. Have a good one, guys.
Scott, I had a quick question.
Uh-huh.
Is the homework up for this week, or do we not have it this week? Or because I couldn't find it.
I am going to put it up soon. I think I should be getting, let me see if he sent it. So I'm probably going to make it due Saturday. If I get it put up today. I was waiting for the course coordinator. I was under the impression that he was sending it, but if not, I'll delay the due date if it's if I get it put up.
Okay.
But yeah.
All right. And then are we still planning on having a quiz tomorrow?
Tomorrow, no. So it would be the quiz I'm going to have on Friday. Okay. Now, most likely. Yeah.
Sounds good.
Okay. All right. Have a good one.
So you think the homework will be up to date at some point?
Yeah, it should be. I need to get it from the course coordinator. I don't know why he hasn't given it to me yet, but yeah. Should be up. Right. So the quiz is going to be it should be over conservative vector fields, the integrals, and then integrals of so surface integrals of scalar functions. So that's 12.3 and 12.4.